Hello, my name is Mostafavi. I'm a PhD candidate at the Computer Vision Lab of GIST. The work I'm going to present is the joint project we had with my advisors, Professor Choi and Professor Yoon. It's titled Learning to Super Resolve the Intensity Images from Events, and it was accepted orally to CVPR 2020. So what are event cameras and what are events? Event cameras, also known as neuromorphic cameras, are new imaging devices that record the differences of intensity per each pixel in their logarithmic scale. So this diagram shows the intensity change for a sample pixel over time. If the intensity goes higher than a predefined threshold, that pixel location together with its timestamp is reported as a positive event, colored in red. If the intensity drops and goes lower than a threshold, it's reported as a negative threshold, colored in blue. Together with its timestamp, it's reported and with the pixel location. And this will create a stream of outputs. Event cameras can offer vision with large illumination changes, vision under extreme low light conditions, vision in rapid movements without creating motion blur, and also they're useful for high-speed motion detection. Traditional cameras report images as fixed time intervals. Unlike them, event cameras output each pixel asynchronously up to microsecond resolution as a stream. This stream of event data cannot be delivered to image-based vision algorithms or neural networks as they expect tensor-like representations, so we aggregate them as stacks based on time or the number of events. Although future event cameras might be manufactured with high resolution, but most current commercial available event cameras have relatively low size resolution, and previous event to intensity image reconstruction methods aim for same size outputs, either using statistical methods or learning-based architectures. What we do is we aim to simultaneously reconstruct high quality intensity images with super resolved dimensions using our recurrent residual design. We use a sequence of stacks over time as input, which can be 3, 5, or more. The central stack indicates the timestamp of the output intensity image. We take the central stack and its next stack together and feed them to our flow estimation network to make the optical flow between the two stacks. This flow plus the stacks go to an event feature rectifier, EFR, to make the events have sharper edges. These rectified events plus a previous state go to the super resolution network, SRNet, to make the next hidden state and also an intermediate intensity image output, IN plus M. This process is repeated with the previous stack as a pair with the central stack, and also the central stack by itself to make IN and IN minus M. All these intermediate intensity images are mixed in the last stage through this mixer to create the final output image, ON. At training, we compare this output with the ground truth using our similarity metrics. The SRNet, which is responsible for the super resolution, is a combination of 4 residual networks, which has RNet A as its deepest design. So we designed these connections so that the reconstructed image mainly relies on new incoming events, while also considers previous states. Our data set is from 2 sources: real-world events with same-size images from event cameras and simulated data created using the eSIM simulator. The real-world cameras usually are infused with an active pixel sensor, or APS, which is a standard intensity camera and shares the same grid line with the event pixels. Unlike the APS frame from a real-world camera, the simulator's ground truth has high dynamic range properties. It's immune to motion blur and has no limitation on ground truth size. So we mainly use the simulator for training, but for testing, we use both simulated and real-world data. On these real-world events, we compare our reconstructed images to the state-of-the-art by downscaling ours. On the simulated data, we compare our super-resolved outputs to state-of-the-art event-to-intensity image reconstruction combined with state-of-the-art single or multiple image super-resolution method to make them have super-resolved dimensions. So these are some of the qualitative results on the same size reconstruction and also on super resolved reconstruction settings. These are for real world, and we also have them for the simulator. And EV is the state-of-the-art event to image reconstruction. And over here, EG is our previous CVPR 19 paper. And the quality of our new method is much better than the previous ones. We also show the performance of our method on some challenging high dynamic range sample real sequences in which our method reconstructs higher quality images in comparison to other methods under diverse challenging illumination settings. We use real world and simulated sequences and show that we outperform previous methods on average in terms of the structural similarity, mean square error, and a learned metric called the perceptual similarity, or LPIPS. We also, so that's for real world, and for the simulator, we also do it. And furthermore, we compare our results to EV combined with two recent single image super resolution and multiple image super resolution so that their size will also be super resolved. We do it on the 4 times super resolving setting, and we show that our method has better quality outputs. So to ablate our loss functions, we have L1 and LPIPS loss, and we use the combination of these two because it has less artifacts and creates better outputs, which the numbers also prove that. We further extend our method to also use APS frames, and also we could double pass through the network to even create higher quality images. These are some samples of our dual passing. As you could see, the quality on the Zoom version is much better in comparison to the APS frame, or even the complementary frame together with events can create details that the APS frame cannot. For the failure methods, if the front moving events are very fast, we sometimes miss background details. I encourage you to use our code to create some outputs using this QR code or this link, and the paper is also available there for more details. Thank you.